Thank you. So this talk is mainly about perseverance in two senses. One is me doing this. I have to persevere a lot to actually achieve it. And the other sense, because it's all about perseverance, what we are doing here. Imagine a slightly different task than what Maciej and Robert presented before a second. Imagine a situation where you don't have a training set and a test set, validation set. You don't even know how to classify anything because there's nothing to classify. But instead what you get is you're getting rewards for taken action, just like in the real world. So this little pig here tries to climb up the stairs, and it doesn't know when the stair ends, if at all. But the hope is that the reward is there. And if it perseveres long enough, it will achieve the reward, and it will win the game, if the game is. But if it doesn't, then, oh well, it will not. Just like in real life, right? You take actions every day, you get a reward, but the reward is delayed. You learn today something that may or may not be useful in 2 to 5 years from now. So yeah, I'm Maciej Jaśkowski, and I'm a data science freelancer. I used to be a programmer. I used to do some stuff for different companies, mostly startups. And lately I've been to Recurse Center, and that's where I started to experiment with deep reinforcement learning. And it's deep reinforcement learning we're going to talk about. But first, let's see what reinforcement learning in general can do for us. So let's try to play the video. Oh my god, where is the mouse? Can you see the mouse? Oh, there is the mouse. Oh, it doesn't work. The touchpad doesn't work. That sucks.
You have to learn the mouse.
Oh, another problem solved. Controls.
Does anybody has a mouse? Anybody?
Can you go just to YouTube, type it in how to play well, autoplay like there. Wystarczy Ctrl T, YouTube. Tak, autoplay. Tak, ale zepsuliście. That works for me.
Długo się uczy.
To działa, tak? To działa.
Oh my god.
Lewo jest prawo, prawo jest lewo.
To add to technical problems, right? So we tried all of these, and they didn't work either with my computer. Anyway, let's
Space Invaders.
Okay, almost right. Let's start somewhere here. So this is. I can actually full screen that, can I? Yay! So you can see, for example, a reinforcement learning algorithm that learned to play table tennis. It's probably not mastering that. There is no mastering what he's doing, but he still does thing. And if you imagine that, if you understand that the input to this algorithm is basically what a camera here sees. Damn it. what a camera somewhere here, I believe, or somewhere here, sees. So there must be a camera that's the only input, the camera, and then it gets the input that, oh, you scored or you didn't score. And nevertheless, it learns quite a bit. Just look how the arm needs to move. There are a couple of points that needs to that can change their position angle here, here, and here, and it all works. It is quite amazing. Or if you work for Google DeepMind, you can use actually deep reinforcement learning to play Go, and actually win with Master of Go, which was Fan Hui, I guess. Sorry?
The name of the guy.
I guess there were more than one. Well, whatever. I mean, in one of the papers they said about Fan Hui, but maybe there was another match. I'm not sure. And
before that, there was a match with European champion, by the way, also from China. It was 5-0.
Yeah, very interesting. Thank you. Or you can try to use the same techniques actually to achieve something completely different. And in this case, the actions that were to be taken was to choose a part of the image that the algorithm is looking at. So if you imagine how you look at the world, you see something very, very sharply, but there is vast space where you understand what you see, but, well, you don't recognize faces anymore, you can't see the people exactly, but you still can see them. So that's what people here try to do, and they try to say that, okay, so let's take an image, and let's pretend that we only see a part of this image very sharply, and the rest of the image with less, well, with a bit of blur. So for example, here you can see a number 2, and you can see that far away from the center, the digit is blurred. Now, the task of the algorithm was to recognize these digits, just like that. But it was never presented the whole image like that. It was rather presented, it was choosing places to look at with this sharp window. And it turned out that by doing this, they actually achieved better results than if they look at the whole image at once. And the results are even better if some noise was added, because then the network could actually focus on the digit itself and ignore the noise that you got here. So I did neither of these. I actually played some Space Invaders. I actually taught. I taught my neural network to play Space Invaders, and we can see how it goes. No, I will not make it full screen, sorry, because it's going to be a pain to get out of it. Yeah, let's watch. Well, this is actually a game that was recorded probably a month ago, and since then I made it a little bit better than that. But still the AI was able here to achieve on average, some 550 points, so, which is as good as I can get, actually. Which means also that every now and then it was capable of finishing the level and start off the other level. And what I did was based on the, well, I should say, classical work of Maciej, Silver, of cumulative control for deep reinforcement learning, which is exactly what I'm going to talk about. So, where is the mouse? Yeah, so I implemented that. You can actually find it on GitHub. So by the way, these slides are available online, so you can go there even right now and, I don't know, scroll them yourself, play the videos yourself if you wish, on full screen. But there are other implementations out there because it's nothing really novel. There are, so I actually implemented in Tiana and Lasagne. There are other implementations in Tiana and Lasagne, and like I never used them, but I suppose they are better. At least, whatever. I mean, you can check it out yourself. And there are some other implementations in Lua, in Cafe, in TensorFlow, I guess too, but I didn't find any. But I wasn't looking for them either, so that's why. So how does it work? What do we've got? So let's try to wrap up what our setup is again. So we've got an emulator. In our case, it's the game of Space Invaders, and what we get is a screen, a frame, and what we need to do is to take an action. And given a frame, if we take an action, we put it into an emulator, and in return, in response, we get a new frame. The next frame of the game, number of points that we got in this transition, and the information whether we lost alive or not. So of course the reward might be, like I mentioned before, might be very delayed, in the sense that if I'm shooting a laser beam here, the information that I actually killed someone, I will get in many frames after that. And this is a challenge. Yeah, let's start with that. So what we need to do is we need to find a strategy, a policy that, given the frame, will give us an action, just as easy as that, right? Nothing really complex. But to do that, what people usually do in like classical reinforcement learning, and we're going to do this too, is to somehow measure how, we need to somehow measure how good a current situation is. Just like you play Go or you play chess, and you take a look at the board and you're like, oh, that's pretty good, it's reasonably good, I'm gonna win. Or, oh, it's really bad, I'm not sure if I'm gonna win, right? We get the same here in Space Invaders. Either the laser beam is coming right at us, and you're like, oh, I'm gonna die, or you're like, I just shot like thousands of laser beams and I'm gonna win the game, right? So we need to have some way of like weighting this, some way of saying, yes, it's like, oh, I'm gonna score at least 10 points more, or I'm gonna score like on average 9.7. Right. Once we have that, that's very easy, because we can simply say, okay, so let's take the best action possible in the current situation. No. Maybe later. So how we are doing this? Well, we are using here a neural network, so we are actually applying a neural network to the screen, to the frame. Why we are doing this? Because neural nets are so good at compressing the information, right? So we just want to compress the information from the images. A lot of redundancy on the image, and the actual information is pretty sparse. So we have here 5 layers of neural networks: 3 convolutional layers, 2 dense layers, and the output of so again, the input to this layer is simply the image, but the output of the layer of the network is basically our Q function here, which means that the neural network, if for example in Space Invaders case you have 4 actions you can take, you can shoot, you can go left, you can go right, or you can just do nothing. So you would have, so your neural network would respond with 4 numbers, and each number would correspond to one of these actions that you can take, and it would be like the expectation. What do I expect from the future, right? Now, there is a slight problem here, because to train a neural network, if we have it trained, then well, we can use it, right? It's gonna work, maybe. But how to train it? We don't have a proper loss function that we don't have a proper loss function. Now we expect Microsoft Windows update, right? So we don't have a proper loss function. We don't have like the Y's. We don't have information whether it is. I mean, we're gonna output something from this neural network, and how to say if the output is good or not. How to measure that? That is a problem. And but if you think about it, we said that the Q function should be something that predicts like the expectation. What do I expect from the future if I take this action? So imagine that you have taken this action, and you're in the new somehow state position, and you see the world again. So you apply our neural network, and you say, oh, now I see the world completely differently, right? I have taken this action and expected to reach like 10 points. I have taken this action, now I expect only 5 points. So this is like a surprise to me, right? It's like in the real world, you try to cross the road and a car hits you. Well, that's a surprise, right? You've taken an action, you have moved on the street, and then the car hits you. Like, oh, that was surprising, right? That's surprising. And if you see the surprise, then it's probably something that should make you think, oh, maybe I should have changed. Maybe I shouldn't actually have walked on the street, right? And it's exactly the same thing here. You can, once we have our cue, our expectation from the current state and action, then and we take this action, and the emulator shows us the new state. Then we can take a look. Okay, so what are my expectations right now? Now in between we have caught or not every word, and the difference between those two. So the difference between kind of the expectation in next state and the expectation in the current state is a surprise. So we have actually mathematically defined a surprise, which is good because in the neural network we can treat the surprise as a loss. And if we have a loss, then we can backdrop and we can actually teach the network to do something for us. And that's exactly what you're doing. Now, there is a couple of problems with this. So I said that you work with a single frame. But if we work with a single frame, then we can't say whether the laser beam is actually going up or down, right? We don't see this. So what you want to, but if you have a couple of frames, then obviously you see, right? This one goes up, those two goes down. So how to make it work? So in typical convolutional neural network, you put different channels of your image, like red, green, and blue channel of your image, as three channels of the input of the input to the first convolutional layer. What we do instead is we completely neglect the colors because the games are easy. We don't care. I mean, the grayscale image is completely fine. But but instead we put like consecutive frames in these channels. So when a filter of convolutional layer takes a look at this input, it doesn't take a look at different colors, but it does take a look at different frames in time. So we actually included, it's like a brute force include of time into convolutional layer. So you can imagine that this laser beam here, it moved here, so it means that the neural network should see that on one layer, on one channel, there is a laser beam, on the other channel there is only a little bit of laser beam, and on the yet another channel there is no laser beam anymore, basically. Right. And there is a lot of tiny details, and that's the point where we come back to perseverance, because I don't know how about you guys, but when I do these things, it never works at the beginning. You just start doing this, you put something together, finally it works, and it doesn't work. I mean, it compiles, it does something, and in the worst case, it like throws not the numbers at you. In a slightly better case, it tells you, well, I have learned in like 5 minutes, and I'm not going to learn anymore, so what do you do then? And lots of stuff like that. And that's all because there's a lot of, many details that you need to go through. And if you don't get them right, then God forbid, you're not going to make it. I mean, probably it's easier if you have like 1,000 machines and you can just try them out. I don't. So I was looking at the code for a long time and debugging it. So there's a couple of things, a couple of details that are somewhat relevant. I mean, they're very relevant, but some of them are really interesting. So first of all, we're using mini batches. This is not a surprise. We need to use mini batches to use stochastic gradient descent in neural networks, because otherwise it's just not going to work. But what kind of mini batch can we take? I mean, should we take like 32 lost frames that we saw and simply put it into the neural network? Well, that's not going to work, because those frames are highly correlated, and stochastic gradient descent is based on the assumption that the images that you input are actually not correlated too much. So that's not going to work. So instead what we need to have some kind of memory. We just store like millions, bazillions of previous experiences, so previous frames, previous rewards, and etc. All the things that we need in order to just sample from it and put the sample as a mini batch. Now, there are different stochastic gradient descent methods. Maybe I wasn't aware of that really before I started this project, but there are. And one of the most, I don't know, one of the best right now is so-called RMS prop. I have no idea what it means, but that's what it's called. But there's a slight glitch. You can see, for example, RMS prop implemented in lasagna and everywhere, and it doesn't work as well. I mean, I used the lasagna RMS prop and I arrived at 400 points. I was so happy to see, oh my god, I'm better than like a dumb random. Random is 180 points, and a stupid algorithm that keeps shooting like a baby got like 240. So when I was 400, I was like, oh wow, I have killed it, right? But not really. And so it turns out that there is another RMS prop algorithm that's completely never described properly. But if you use it, you gain from 400 to 550 points, which is like, oh wow, that's impressive, right? Just a stochastic gradient descent, just a different method. Now there's also this thing about target network. I'm gonna completely skip it. We talked about that, and oh yeah, and there is of course this. There's this thing about exploration. So reinforcement learning, if you've heard about it before, is always about exploration and exploitation. So we need to explore a little bit to know what to do best, right? What actions to take to actually win. Because if you do not explore, you just stay in the same. You don't have any new information about the world. So indeed, like the whole thing wouldn't work if there was no exploration. So what you do is actually you flip a coin before taking an action. You flip a coin, and you decide whether you take an action at random or you take an action that you think you should take. But this is detail. Oh yeah, this is about the stochastic gradient descent. So you can see here 6 methods, and the red one is actually traditional stochastic gradient descent. So you can see how slow it is when it's looking for the minimum. Anyway. Yeah, I think we're getting there. So I was using Piano and Lasagna, as I told you. I was training this on AWS on spot instances, which was fun. So to train Space Invaders to like something like 700 points on average, it takes about roughly like 36 hours or 8 million actions that the algorithm takes. Yeah, up to now I run like 40 rounds. I'm actually running a round right now, and I hope it's gonna achieve something like 1,000, but who knows? It's better with, I mean, it learns faster, which is a good sign. Yeah. Do you have any questions?
We, who are you referring to?
So I'm just saying, like you said we during the, so I'm just wondering, is it a company or what?
Oh, me, myself, and I, right? Yeah, me and my company, which is me and me. Yeah.
So you mentioned a different version of RMS probe, and how does it differ from the original one from Hinton's slides? Which is probably the one implemented in Lasagna.
Well, I can't show it to you here on the slide because I don't have my computer attached to the projector, but
I like the idea.
From the top of my head, Hodor. I have no clue. Like, I know really. There's I'm well prepared, right? No, I guess in Lasagna the trick there is this parameter called raw, and one of the things is that actually in the RMS prop that was implemented originally for this paper, there are two parameters. So there's one parameter raw that's used as raw or 1 minus raw, whereas in this implementation they actually use raw and raw prime, which is like whatever, I have a clue, but it works, you know, like with all these algorithms, by the way, I mean, don't look at me like that, I don't know why they work, nobody does, right? Like, literally there's this guy, Karpati at Stanford University, he has this very good lecture, by the way, which I have some resources here, do I? Oh, I don't, but there were some links before. Anyway, so he like, literally says, oh, so by the way, here's this RMS prob, it's nowhere actually published. You can take a look at the slides that Robert mentioned. And by the way, so here we have the square root of something, and just for you to know, if you omit this square root, then it's not working. But do we know why? No. It just doesn't.
Was the architecture precisely the one we've seen on the slide? I'd like to hear a few words about the architecture, whether it was particularly just convolutional neural network, you put just 3 consecutive frames, for example, 3, I don't know, into your network, and that's all, and some convolutional layers, and some fully connected layer, and that's it? Okay, I'm just impressed by the simplicity.
Yeah, well, I need a microphone, I don't. Yeah, so remember that this is the trick.
Yeah.
And
I'll tell you better.
And here are many. Where are the tricks? There were some tricks here. Where are they?
Order.
I can actually use this. Where is it? Oh, details, right here. Here are some tricks, right? And these are not all tricks that were there, but I guess the most important ones. I believe. Yeah.
One more question. In the back.
What pre-processing have you did, and what exactly was state in this network? Because in the original paper there was mentioned frame skipping and something like some tricks with it. I'm not sure. I'm trying to replicate the results myself and without success. So maybe I have a problem with this.
Sure. So what were the questions? What was the pre-processing, right? Frame skipping, and there was another question. Okay, two questions. So yeah, it's all about perseverance, right? It didn't work for me at the beginning too. No, the pre-processing I did was the standard one, but actually I'm running right now an experiment because I did slightly different pre-processing that I did, and it might actually turn out that the pre-processing that they described was very important. So the basic pre-processing was to scale the image. So instead of taking the whole image, which is 320 by 160 pixels, I believe, you scale it to something like 84 by 84. And then you take a grayscale of that. You don't take a color image, you take grayscale, and then you stack 4 frames, one on top of the other. And because it's Space Invaders, there's some bug in the Atari, and which means that the laser beam is actually flickering. It's flickering. So there was another pre-processing that was just taking 2 consecutive frames and maximizing, taking the maximum values of all the channels, of all the pixels, to get rid of this flicker. And that's it. Actually, the pre-processing was reasonably simple. That's the whole point, that we don't need to adjust the algorithm to different games, to different inputs. We can just use it. Of course, with completely different tasks that weren't Atari games, you would need to use probably slightly different neural network, because it seems that the sizes of filters are somehow somehow adjusted to exactly Atari games, and there is one of many reasons why your implementation might not have worked is so-called gradient clipping trick, which is basically saying, so by the way, so we have calculated gradient for you, right? I mean, yeah, we have calculated gradient for you, right? But you know, it's like, we don't like too big gradients, because if we have very big gradient, then our neural network is gonna blow up, it's gonna explode. So if the gradient is too big, we're gonna just clip it and say, oh no, you're not so big that you thought you are. You're actually much smaller, and this helps to stability a lot.
Here we can see these pictures, but actually the information on the picture is very simple. We can describe every minion by like 2 numbers, our position with an X numbers. I mean, each of the screen might be described with like 100 digits. Did you possibly try to transform these pictures into such a shorter information, like interpretable vector of digits, and then use some machine learning on this?
No. And the reason is because I wanted to make it, you know, to use exactly the same algorithm for different games. Previously, that's what people used to do. They were taking a game and were like, oh, we're gonna use reinforcement learning because that's what we do to solve these issues. There's nothing new. But they were like, okay, instead of neural network, because we don't know it's gonna work, or previously people were using shallow neural networks, so we don't need like one hidden layer or something, and it wasn't like so we didn't have this nice feature of compressing of neural networks. So and then to actually make it work, people were doing much more complex pre-processing to make it all work. Yeah. So, by the way, about the pre-processing, there is actually another paper that uses, instead of doing all of the pre-processing, they are using LSTMs, and then you don't need to stack the consecutive frames to a channel. We actually just put it into LSTM, because that's what LSTM does, right? It remembers the past. And actually the results weren't better. I mean, on some games the results were better, on some others they were slightly worse. But it's nice that you can just get rid of all the pre-processing whatsoever.
Any more questions?
Could return to this slide for Q function, this recursive formula. Okay.
Which one?
This one. you will see only from S0 to S1. In some games like chess, you need to sacrifice something to win. So the S1 evaluation will be maybe a little bit worse, and you will see result like many moves later. Did you consider to use some more complex formula than this?
This is actually an interesting question. So we can try to get down here to understand it slightly better. The short answer is no, I didn't try. It actually might not be that bad idea. There's a couple of caveats with that. There's a couple of problems with this approach. I'm actually like thinking very hard how to make it work because I started a couple of days ago. But well, the reason why it works is exactly because the Q function is very good at saying us what's the expected outcome in the future. So the Q function, in an ideal world, if we could precisely define the Q function, we would say that the Q is just the reward plus all the rewards until the termination of the game, discounted by some parameter gamma, which is between 0 and 1. And this is, by the way, very nice because it means that if gamma is close to 1, then we value very much the rewards very much in the future. If gamma is small, then we're basically saying, oh, I mean, we're going to focus on the next couple of steps, but we're going to completely disregard what's the future, right? Because if gamma is 0.1, for example, then in like 10 steps, it basically vanishes off, right? So this would be in the ideal world, but if you think about it, it's exactly like saying that we're taking the action and we're looking in the future. So that's why we have here this, we're looking at the Q at the next step. So basically, in the ideal world, it wouldn't matter because we know just as much, right? We don't need to do any more evaluation. But actually, there is so-called TD lambda algorithm. So this is basically like temporal difference algorithm, Q-learning, whatever, if you wish. But there is this thing called TD lambda that would take into account that would take into account a couple of steps more in the future, and it actually helps in many games. Now here, the problem is
computation power is expanding this scenario probably.
I mean, I would like to try even with like 1, 2, 3 more steps. Why not? It could help. But the problem is with correlation again. You have a couple of frames more. You want to learn them, but all of them are high correlated. So how to? I guess it's a technical issue how to get rid of this correlation, how to make it work actually. Yeah, it's an interesting question.
Any more questions from the side, or we can move all discussions to the after party?
Thank you very much.
Thank you so much.
Thank you so much, Maciej. Okay. Right now we're going to move in a while to Świeżo Malowane, which is the place